Number 8. So, number 8 looks like the following. You got a sort of a rampish slide thingy. Starts steep, levels out, comes back around, and then does something like that. Up here is a little box that's going to slide down and go woo, and they call this point P. The height from here to the ground is H. Of course, this is the ground. When the block is here, it's considered to be at point Q. The radius, this is a circle with radius R, which means that the height at Q is also the radius R because it's level with the center of the circle. And that's it. I am going to call this T for the top of the loop, which they don't label, but they ask questions about it. So, Given's mass of this little blocky block is 0.032 kilograms. Radius is 12 centimeters, but we're just going to immediately convert that to meters. Good habit to get into before you forget. And the height h is 5 radii, 5r, which is 0.6 meters. 5 of these. Part A. Part A, we need to find how much work does the gravitational force do on the block as it goes from P to Q, so from this height to this height. So, work through gravity is mg delta y, and let's just substitute in. So mass is 0.032, g is 9.8. Delta y, now we're going from P to Q, and so as you can hopefully see, the whole height from P to the ground is h, Q is r, so if we subtract an r from h, we'll get it. So h minus r. This is definitely not drawn to scale if h is 5r. This doesn't even look like 3r. Should be way up here, but you get the idea. So 0.042 times 9.8 is a times h is 0.6 minus r, which is 0.12, and that equals 0.151 joules. So just sleepy. Just the work due to gravity. Gravity is a constant force, so work is for constant force is force times displacement. Part B. What about from the work from P to the top of the loop? So that's P to T. Work G is going to be mg delta y again. And it's going to be the same thing, but times h minus 2r, because T, as you can see, is 2 radii up. So this just equals, that's all the same, 0.6 minus 0.24, and that's going to equal 0. Oh my god. The yawnings can't stop. 0.113 joules. I apologize if I am making you yawn through contagious methods, or whatever the word is. Part C. Part C, we need to so at the bottom of the loop with the ground, we are defining zero potential energy. So with that in mind, what is the potential energy of the block at point P, way up here? Well, work and potential energy are intimately related. In fact, this is really, it's just the same thing, same expression. So we're just going to do mgh, because it is h up h from the ground. And that's going to be, well, don't need to do that. Well, I'll just keep going now. Erasing is bad in this. H is 0.6. These little quotations mean that these two values are copied down. So the answer is 0.188 joules. Pretty straightforward. D. What is the potential energy at point Q? Q is just a distance of r up from the ground. So UG is going to be mgr, which is 0.032 times 9.8 times 0.12, and that's going to equal 0.0376 joules. 6, and that should be closer. Part E. This problem is E for endless for E. We want the potential energy at the top of the loop. Top of the loop is 2 radii up, so 0.24. That's going to be 0.0753 joules. And finally F. In F, they're asking if instead of merely being released, the block is given some initial speed downward, how do they do the answers? And if so, how do the answers change? Blah, blah, blah. And if so, how much, or how do they change? As you can see, none of these depend on velocity. They only depend on your location or configuration, as stated in the notes with I guess that was conservative. No, I said that in the conservative force notes, so it's not on the main concepts, but it is the configuration. So the values are unchanged because potential energy U has nothing to do with velocity, just location. I don't like this tablet. It's supposed to be better than my old tablet. Yeah. Alright, bye-bye.